Good day everyone, welcome back to another wonderful tutorial class, and today we are going to be looking at a very important topic in physics, and we are looking at heat and temperature measurements, the effect of heat on bodies, solid, liquid, and how to measure the temperature of a body. So now we are going to start with the topic temperature measurement before we go to expansion of body due to change in temperature. Now before I start, ensure you don't skip any part of this video and ensure you watch this video from the beginning to the end in order to get the full details of everything we are going to be explaining here. Now there is something very important you want to do for me. Ensure you share these videos to others. It's very important. Ensure you share this video to others. And swear, like the video is very important. Just try and like it. Click that like button and that like icon. Also try and click on that subscribe icon. It's not going to cost you anything. It's just you are just something like adding to our fame, the fame of this channel. So please try and do that, and God bless you and do that. Now let's look at temperature. Now, what is the meaning of temperature? Temperature, as I said in the elementary physics, that is the degree of hotness and coldness of a body. Now, what is the meaning of degree of hotness and coldness of a body? It means that temperature is a physical quantity or property that characterizes the state of thermal energy in a body, or that characterizes the thermal state of a body. Now, what we tell us the amount of heat that is inside the body is when you measure the temperature of that body. When the temperature is very high, we say this body the heat content is high. When the temperature is very low, we say the heat content is low. So what characterizes the heat energy in the body is so-called temperature. So temperature is a physical quantity or property that characterize or give the thermal state of a body. Now, this temperature can be measured by an instrument called a thermometer. It can be measured by what? By an instrument that we call what? A thermometer. Now, take note of that. Thermometer is the instrument used for measuring the temperature of a body. Now, temperature is a physical quantity. Remember, we did physical quantity in this channel before. We said physical quantity are any measurable quantity in physics. They can either be fundamental or they will be derived. Now, temperature, is it fundamental or derived? Temperature is a fundamental physical quantity. It's a fundamental what? Quantity. And the unit, the fundamental unit of temperature is what we call Kelvin. Take note of that. The fundamental unit of temperature is what we call Kelvin. And it is a what? Temperature is a fundamental quantity. Also take note of that. It's very important. We have other units of temperature like Celsius, Fahrenheit in different scales. Now, listen. When three bodies, that's what we call Zeroth law of thermodynamics. Zeroth law of thermodynamics is still very important in this temperature measurement. Now, what is this law? Remember, we have first law, second law, third law, and Zeroth law. Although we are not doing thermodynamics now, but I'm just going to introduce what we call the Zeroth law of thermodynamics to you guys now. Now, what does this law state? It states that if two bodies are separately, let's say two bodies A and B are separately in thermal equilibrium with a third body C. With a third body what? C. If this body is the thermal equilibrium with this, and this body is the thermal equilibrium with this, therefore bodies A and B are also in thermal equilibrium. Let's say, now what do we mean that bodies are in the same or they are in thermal equilibrium? Now, remember, take note of this. Two bodies are said to be in thermal equilibrium if and only if their temperature are the same. If the temperature of two bodies are the same thing, it means that those bodies are in thermal equilibrium. Those bodies are what? They are in thermal equilibrium. Now, states that, Zeroth law states that if two bodies, let's say A and B, are separately in thermal equilibrium with the third body C, therefore bodies A and B are also in thermal equilibrium. This law throws light on the thermal equilibrium between bodies or systems. The heat equilibrium between bodies or systems, and two bodies can only be in thermal or heat equilibrium. That means they have the same heat if and only if their temperature are what? are the same. You take note of that from this law, from this law, from this law. Now, there's what called scale of temperature. Scale of temperature. Now, what's the meaning of scale of temperature? A scale of temperature is just something like a definite number on an arbitrary scale in which the degree of hotness and coldness of the body can be expressed. In which the degree of what? Hotness and coldness of the body can be what? Can be expressed. Now, before you calibrate a thermometer, or before you mark out a temperature scale, the scale of temperature, when you mark it out, there are some procedures you are going to follow. Now, what are these procedures? What are these what? Procedures. Procedure one of them is you must give up, you must something like choose a body or a substance with a defined thermometric property. Whatever, defined thermometric property. Now, what is the meaning of thermometric property of a substance? We'll get there. We'll get there. Now, also, you are going to mark out what we call the upper and lower fixed point. You're going to mark out what we call the upper and what? And the lower fixed point. Now, what's the meaning of upper fixed point? What's the meaning of lower fixed point? Now, the upper fixed point of a scale is the point the scale will read when it's placed in boiling water or steam. When you place a scale or a thermometer in boiling water or steam, so let's steam, and the value that thermometer will read, that is what we call the upper fixed point. The lower fixed point is the value it will read. It is placed in melting ice water. When it's placed in what? In melting ice water. In melting what? Ice water. So you're going to mark out the upper fixed point, mark out the lower fixed point. And as I said, you will choose what? A body with a defined thermometric property. Now, what is the meaning of thermometric property of a body, or what is the meaning of thermometric property of a substance? This is a physical property. What we call a thermometric property is actually a physical property. Is actually what? A physical property that can vary or change in a known way with temperature. That can vary or change in a what? In a known way with temperature. And it can also be measured by means of gauge temperature. This property we are talking about, that we are calling thermometric property, is that property which is physical. Is the physical property of a substance that can change or vary in a known way with temperature. We have different properties of a thermometric property of a substance. One of them is the length of liquid column in a glass capillary tube. I said what? The length of what? Of liquid column in a what? In a glass capillary tube. We have another one, number two. The pressure of an ideal gas whose volume is kept constant. That's what the thermometric. The pressure of what? Of an ideal gas whose volume is what? Is kept constant. We have another one, which is the electric resistance of a platinum wire. The electric what? Resistance of a platinum wire is also a temperature of a substance of the body. You also have what we call the electromotive force of a thermocouple, etc. We have so many of them. We have so many of them. Then also what we call the useful temperature scales. We have the useful temperature scales, and one of these scales is the Kelvin scale. 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 Now, what is the meaning of Kelvin scale? What is the meaning of Kelvin scale? What is the meaning of Kelvin scale? Now, this scale is also known as thermodynamic scale. Take note of that. This scale is also known as what? Thermodynamic scale. And it is based on the theoretical efficiency of a perfectly reversible heat engine. This scale is what? Is based on the theoretical efficiency of a perfectly what? Reversible heat engine, not practical. And the upper fixed point of this scale is 2373.16 approximately, or 370.15. If you have Kelvin, if you approximate it, it will become 373 Kelvin. This is the approximate value. So sometimes you write 373.16, or write 373.15, like 12, 13, and so on. But approximate value in whole number, not having decimal, is 373 Kelvin. That is the upper fixed point. What about the lower fixed point of this scale? Is 273.16 Kelvin, which is approximately what? 273 Kelvin. But some can be write 73.12, 0.15, 0.13, and so on. But approximate value is still 270 Kelvin. That's the approximate value. So this is the lower fixed point of Kelvin scale, is the upper fixed point of what? Of Kelvin scale. Then we also have another scale that is called the ideal gas scale. We also have another scale as well, the ideal gas scale. Now, what is this ideal gas scale? What is this what? Ideal gas scale. Now, for ideal gas scale, the working substance is the fixed mass of ideal gas. The working substance is the fixed mass of ideal gas, and the upper. Okay, let me start from the fixed point. And the lower fixed point of this scale. Remember, the upper fixed point of Kelvin scale is this. While the lower fixed point of Kelvin scale is this. Take note of this. So this is the upper, lower fixed point of Kelvin scale. Now let's look at ideal gas scale. The upper fixed point, the lower. Let me start from lower. The lower fixed point of ideal gas scale is the absolute zero temperature. Absolute zero what? Temperature. Absolute zero temperature. Which is assigned with a value called 0 Kelvin. It is assigned with a value called OK or 0 Kelvin. Now, what is the value for absolute temperature? The value for absolute temperature or absolute zero temperature is 0 Kelvin. Take note of that. Not 0 degrees Celsius. Not 0 having other scale you know. 0 Kelvin. That's the value for absolute zero temperature. Now, what's the value for absolute zero temperature? That would be a food for thought for another day. But the value for absolute zero temperature is 0 Kelvin. Take note of that. It's very, very important. Now, remember the third law of thermodynamics spoke about this absolute zero temperature. When the entropy of a system reduces to this minimum, the temperature will reduce to this absolute value or a constant value. If the temperature of a system reduces to its absolute value, the entropy will take a constant value or reduce to zero, almost zero. Remember, what is not entropy? Entropy is just the degree of disorderliness of the system. So what will reduce at a point in which the disorderliness of the system is now minimal, very minimal, approaching zero. There's no more disorderliness again. That is the point we call the temperature at that point is called absolute zero temperature. You take note of that. It's very, very important. Why the upper fixed point of this scale? Is the temperature of the triple point of every water. Why the upper fixed point of this scale is the temperature of the triple point of every water. Now, why is it not triple point of every water? Now, the triple point of every water is the point at which water coexists in its solid, liquid, and gaseous state. The point at which water will coexist in the liquid, solid, and gaseous state. That point is called the triple point of water. And the temperature at that point is the lower fixed point of Kelvin scale. Is the what? Is the lower fixed point of Kelvin scale. Which is what? 273.16 Kelvin. Approximately 273 Kelvin. Take note of that. Now, for an ideal gas scale, the unknown temperature can be obtained from the relation unknown temperature of T is equals to Pt over Pt arrow times 270.16 Kelvin. Now, what's the meaning of T? T is the unknown thermodynamic temperature. Now, why do I call it thermodynamic temperature? Because the unit is in Kelvin. Any temperature that has unit as Kelvin is called thermodynamic temperature. It's called what? Thermodynamic what? Temperature. That is the reason why we call it the thermodynamic, because the unit is what? Is Kelvin. Any temperature in Kelvin is called thermodynamic temperature. Now, what's the meaning of Pt? Now, Pt is the pressure at the unknown temperature. The what? The pressure at the unknown temperature. What's not Pt arrow? Pt arrow is the pressure at triple point of water. The what? The pressure at what? At triple point of what? Water. No, let's look at this. Take a look at this. Example. Look at example. Look at this one. If the pressure at a particular temperature T Pascal. If the pressure at a particular temperature T is 50 Pascal, and the pressure at the triple point of measured at the triple point of water is 60 Pascal, and the pressure measured at the triple point of water is 60 Pascal. This is the pressure at another temperature T, and the pressure at the triple point of water is 60 Pascal. What will be the value of T? What will be the value of what? Of T. Remember, Pascal is the unit for pressure, which is also the same thing as Newton per meter square. Take note of that. And the value of T we said for ideal scale is PT over what? PT arrow times 270.16. Now we got what is pressure at T? Pressure at the low temperature is what? 50 over what is pressure at the point of water? 60 times 273.16. So this one give us this over this times this. You solve that with the calculator, you're going to have 227.6 Kelvin. That will be the unit. Because the unit of this formula is what? In Kelvin. Take note of that. So this is for ideal scale and so on. Now we also have other scales like Celsius scale. We also have other scale like we also have Celsius scale. Now, what is the meaning of Celsius scale? Celsius scale can also be called it was derived from the centigrade scale. It is also known as the customary scale. We call it the customary scale. So that the what? Also known as the customary scale. And the upper fixed point of this Celsius scale is 100 degrees Celsius. The upper fixed point of this scale is 100 degrees Celsius, while the lower fixed point of this scale, is 0 degrees Celsius. So that means 100 degrees Celsius is equivalent to 373.16 Kelvin, or approximately equal to 373 Kelvin, while 0 degrees Celsius is approximately equal to 273 Kelvin. Why am I saying this? I'm saying this because the upper fixed point for this and this are the same thing. Upper fixed point means the value the scale will read when the scale is placed in what? In boiling water or steam. It's not steam. Steam is the most correct word there, because you have the absolute value, absolute temperature there when it is one of steam. Then another thing is we have other name we can call this upper fixed point. We can call it boiling point. We also call it boiling point, upper fixed point, boiling point. We also have lower fixed point, melting point, or ice point. We have ice point. Ice point is the name, also another name for lower fixed point. Melting point, another name for lower fixed point. Lower fixed point, ice point, melting point are all the same. Upper fixed point, boiling point, steam point are all the same. Steam point, upper fixed point, boiling point, they are the same thing. Lower fixed point, melting point, ice point, they are the same thing. Take note of that. It's very, very important. So we said this is the lower fixed point for Kelvin scale. This is the lower fixed point for Celsius scale. So 0 degrees Celsius is equivalent to 273 Kelvin. Take note of that. It's very important too. The 100 degrees Celsius is equivalent to 373 Kelvin. Take note of that. It's very, very important. So this is the upper fixed point of Celsius scale. This is the upper fixed point of this is the lower fixed point of Celsius scale. For Kelvin scale upper, for Kelvin scale lower fixed point. I will not be getting details into this place. Then we also have what we call the Fahrenheit scale. Take note of that spelling of the Fahrenheit. Fahrenheit scale. Fahrenheit scale. We also have the Fahrenheit scale. Also have the Fahrenheit scale. Now for the Fahrenheit scale, the upper fixed point for Fahrenheit, that's why I don't want to write this one here. The upper fixed point for Fahrenheit, the upper fixed point is, now let's write out the upper fixed point. Now the upper fixed point for Fahrenheit is 212, that is 212 degree Fahrenheit. While the lower fixed point of Fahrenheit is 32 degree Fahrenheit. Check, Kelvin don't have degree, Celsius has, and Fahrenheit. Take note of that as well, it's also very important. Now, this upper fixed point will also be the same thing as 100 degrees Celsius. So this, look at it now, 212, 100, 312. They are all the same thing. The difference between them is that this one is the Kelvin, this one is the degrees Celsius, this one is the Fahrenheit. So water will boil at 100 degrees Celsius, 313 Kelvin, 212 degree Fahrenheit. Take note of that. It's very, very important. Now, for Rankine scale, the upper fixed point for Rankine scale, there's another thing called Rankine scale. The upper fixed point is 672 degree Rankine. That's the upper fixed point. While the lower fixed point is 492 degree Rankine. That's the lower fixed point. That means, look at another thing. Let me show you another thing. This means that water will boil. The boiling point of water is 100 degrees Celsius, or 313 Kelvin, or 212 degree Fahrenheit, or 672 degree Rankine. So this and this are the same thing. The only thing is just their units and different. People of that is very, very important. And vice versa. Now, what's called fundamental interval? Fundamental interval. Now, what's called fundamental interval? Fundamental interval is the difference between the upper and lower fixed point of the temperature scale. The difference between what? The upper and lower fixed point of the temperature scale. For example, now, what is the difference between this and this? It means 212 minus 32, that's 180. What is the difference between this and this? 672 minus 492 is still 180. What is the difference between this and this? 100. What is the difference between this and this? 100. So the difference between the upper and lower fixed point of the temperature scale is called fundamental what? Interval. What do we call it? Fundamental interval. Now, what's what we call thermometers in practice? The thermometers in practice. Thermometers in practice. Now, we have a lot of them. We have constant volume gas thermometer. And the constant volume gas thermometer. We have the platinum resistance thermometer. Then we have the thermocouple thermometer. We have the liquid in glass thermometer, and that be alcohol, mercury, and so on. Then we have the radiation pyrometers. Now, what is the meaning of what's it called? The constant volume gas thermometer. What do you mean? Now, for a constant volume gas thermometer, the thermometric property is the pressure of an ideal gas whose volume is kept constant. The pressure of an ideal gas whose volume is kept constant, and to measure a temperature using this thermometer, temperature will be equal to PT over PT arrow times 273.16 Kelvin. Remember this? We have already studied this before. We were doing the ideal gas scheme. So we use that for constant volume gas thermometer and so on. Then we also have this is majorly from ideal gas scheme. It's also like actually directly from the constant volume gas thermometer. It's majorly from ideal gas scheme. Then remember the temps, the temperature of tea, the temperature of water, and so on. Then this temperature is very slow to use. Cubasol. It's not convenient. This thermometer is not what? It's not convenient. It's very slow to use, and it is Cubasol. It's not convenient. But it is very sensitive and accurate. It's very sensitive and it's also accurate. They also have another one, the platinum resistance thermometer. The platinum resistance thermometer. Now, for platinum resistance thermometer, the thermometric property is the resistance of the platinum wire. The what? The resistance of the platinum wire. From interpolation, you saw that the temperature, let me use theta, on this scale can be measured from the relation that arrow theta minus arrow 0 over arrow 100 minus arrow 0 times 100 degrees Celsius. This one is not Kelvin this time. It's not Kelvin. So please take note of that. It's very, very, very important. It's very, very what? Important. Arrow theta minus arrow 0 over arrow 100 minus arrow 0 times 100 degrees Celsius. Take note of that. It's very, very, very important. Now, what is the meaning of theta? Theta is your low temperature. I can try to say T is equal to arrow T minus arrow 0 all over arrow 100 minus arrow 0 times 100 degrees Celsius. Not in Kelvin. Please take note of that. It's very, very important. So this thing now represents theta here. I cannot use x. I cannot use any value, like as far as it's unknown value, no problem. So this theta and this t is the unknown temperature. Arrow theta and arrow t is the resistance at the unknown temperature. The resistance at where? At the unknown temperature. While arrow 0, anyway, see arrow 0, it means the resistance at 0 degrees Celsius. The resistance at what? At 0 degrees Celsius. What about arrow 100? The resistance at 100 degrees Celsius. The resistance at 100 degrees Celsius. Example. The coil of the wire has the following resistance. Example. The coil of the wire has the following resistance. The coil of the wire has the following resistance. Let's say that's a 2 ohms, comma, 3 ohms, comma, and 6 ohms. 2 ohms, 3 ohms, and 6 ohms. 2 ohms, 3 ohms, and 6 ohms at following temperature 0 degrees Celsius, comma, T, comma, and 100 degrees Celsius, full stop. And the following temperature 0 degrees Celsius, T, and 100 degrees Celsius, full stop. What is the value of T? What is the value of T? What is the value of what? Of T. Can we do that? Can we do that? Remember, this is the resistance. Look at it. This value of expression are respectively given. They are what? Respectively what? Given. That means we have 2 ohms, 3 ohms, and 6 ohms. Corresponding to 0 degrees Celsius, T, and 100. Respectively means the first we take the first here, the second we take the second here, the third we take the third here. That's the meaning. So what is the first resistance here? This one is resistance of 0. That means 2 correspond to 0 degrees Celsius. So the resistance at 0 degrees Celsius. The resistance at 0 degrees Celsius. Resistance at 0 degrees Celsius is 2 ohms. That's the meaning. So the first here is 0. Then the second is T. The resistance at T is 3 ohms. The third one is 100. The resistance at 100 is, third one here is what? 6 ohms. That's what I'm trying to say. So let's impute this value now into this formula to see what we are going to have. Let's impute those values into that formula to see what we are going to have. Sorry about this. Let me quickly just solve it here. Then let's impute it to see what we are going to have. We're going to have our value, the value of T to be equal to, that is the unknown temperature here, Nabi. So the unknown temperature will be equal to arrow T minus arrow 0, arrow T minus arrow 0, all over arrow 100 minus arrow 0 times 273 times 273. Okay, times what? 100 degrees Celsius. Sorry about that. 170 times 100 degrees Celsius. So let's know what we're going to have next. Imputing the values that we're going to have. Arrow T is what? What is the arrow T 3? Minus 2 over what? Over arrow 6 minus what? My arrow 0. Where's arrow 0? Minus 2. 6 minus 2 times 100 degrees Celsius. So this will give us a very good answer. You know, this minus this, that is 1 over what? This minus this, that is 4 times 100. Now what is 1 over 4 times 100? 4 here 1. 4 here, we have 25. This will give us 25 degrees Celsius. That's what we have. 25 degrees Celsius. So 25 degrees Celsius will correspond to T. 25 degrees Celsius will correspond to T. If 2 corresponds to 0, 3 corresponds to this, and 6 corresponds to 100. What you do is just impute the values very well, then you're already good to go. You already what? Good to go. We are going to solve more questions as this class moves on. So let's look at now the what's on that, and this platonic resistor thermometer can also move on more. For the platonic resistor thermometer is the best thermometer within the temperature range. Is the best thermometer within the temperature range of 13.8 Kelvin, 3.8 Kelvin to 904 Kelvin. Take note of this. Take note of this. Is the most accurate thermometer on the IPTS scale. If you check that scale, the best there is the within the temperature range of 13.8 Kelvin to 904 Kelvin is the platinum resistance thermometer. So let's look at other thermometer now and go into how to convert one temperature scale to another. We are still here, so still with the right. So same so-called IPTS scale, which is IPTX scale, International Practical Temperature Scale, International Practical Temperature Scale. Take note of that. And the best temperature thermometer within the range of approximately 13.8 to 904 Kelvin is the platinum resistance thermometer. We'll have the thermocouple thermometer. The thermometric property is the electromotive force of the thermocouple. The electromotive force of the thermocouple, and this thermometer is the best thermometer within the temperature range of 904 Kelvin to 1338 Kelvin. Move to 1338 Kelvin. The temperature within this range, the best one is the thermocouple thermometer. We have the radiation barometer. Radiation barometer is the best when you are moving above the temperature of 1338 Kelvin. You are measuring above the temperature of 1338 Kelvin. So take note that's very, very important. We also have the liquid in glass thermometer. Example of liquid in glass thermometer is the one they call the clinical thermometer. Now the liquid that can be inside this glass, it can either be alcohol or mercury, or any other stuff like useful liquid that has a definite pragmatic property. Remember, the definite property of this liquid in glass thermometer is the length of liquid column in the glass capillary tube. Don't forget that. So the major two type of clinical or the major two type of liquid in glass thermometer we'll be looking at now is the one we call the alcohol in glass and the mercury in glass. Now for alcohol in glass, mercury in glass, alcohol in glass is when you put alcohol inside the glass tube, and mercury glass is when you put mercury inside the glass tube. So that's what we mean by the alcohol. The one that is made up of mercury is the mercury in glass. The one that is made up of alcohol is the alcohol in glass. Remember, alcohol boil temperature of 78 degrees Celsius. So between these two temperatures, now which one do you think will measure a higher temperature? The one that will measure higher temperature is the mercury in glass thermometer. So mercury will measure higher temperature than alcohol. Because alcohol has something like constant 2 degrees, something like a boiling point that is not even up to boiling point of water. So take note of that, is very, very important. Then we also have the one that measures a very low temperature. A very low temperature. Alcohol can measure a very low temperature more than the mercury in glass thermometer. Now, you go and do something for me now. You're going to do something very nice. Go and check for the thermodynamic property considered. If you want to choose alcohol as something like a thermodynamic substance, the properties you're going to consider. If you want to choose mercury as a thermodynamic substance, the properties you're going to consider. Go and look at those terms. They are very, very important. Go and check the properties of those, the physical properties of those substances you're going to consider before choosing them as a thermometric property. Go and do that for me. Then go and look for the advantages and the disadvantages between alcohol in glass and mercury in glass. For example, now one expands more than the other, while one has higher conduction more than the other. Look at them, it's very, very important. For example, now one can wet glass, while the other will not wet glass. One have problem of fix, something like this. You cannot easily see it, opacity, something like it is not easily seen inside the glass because it's white and the glass is also white. So one has that problem. Remember, alcohol should have that problem. The one that wet glass should be alcohol, alcohol should be the one wetting glass. Because mercury actually is a metal, but it's something like a liquid metal at room temperature. I don't know if you can remember that. The only liquid metal at room temperature is mercury. I don't know if you can remember that. So that is just that. So we're going to look at interconversion of temperature scales. Interconversion of temperature scale. How to convert from one temperature scale to another. Let me show you how to convert from one temperature scale to what? To another. So let's get something. Number one, let's how to convert from Kelvin and Celsius. How to convert between Kelvin and Celsius. Talk about between Kelvin and Celsius. How do you do it? Between Fahrenheit and Celsius. How do you do it? Between Rankine and Celsius. How do you do it? Between Fahrenheit and Rankine. How do you do it? Between Fahrenheit and Kelvin. How do you do it? So that's what we're going to be looking at now. Now let's say I talk about between Kelvin and Celsius. How to do it? Any of them. How to do it? You draw a scale for both of them. Draw scales for both of them. You mark out their upper, lower. Upper, lower. Upper for Kelvin is 373 Kelvin. Lower is 273 Kelvin. Then upper for Celsius is 100 degrees Celsius, while the lower is what? 0 degrees Celsius. So you mark out this one to read in Kelvin, the 0 degree. Mark out this one to read in degrees Celsius. Then you don't use interpolation to round up everything. How do you use interpolation? You solve a particular mathematics here and repeat the same thing in this place. What is the meaning of that? Now can you say, like me, I like saying this. I will pick the unknown. Look how I do my interpolation. I'll pick the unknown inside this way. It must be 1, 2, 3. It should not be more than 3 or less than 3. That's it. And it's not always, it is always 3. If it's less than 3, you have to remove one. It means one thing is wrong inside. And because you are measuring something, those are the 2 things you already know inside. Only one thing will be unknown there. So what I do there, I'll never pick the unknown inside. And I'll remove lower fixed point from that unknown. I'll pick the upper fixed point, then remove the lower fixed point, then divide it 2. For example, I'll pick this scale, I'll remove this 273, then I'll pick this one, then I'll go to divide it 2. I'll pick this upper fixed point 373 minus the lower fixed point 273. That's what I do my own. So you can also be doing your that way. You just pick the unknown, even though the unknown is here, pick the unknown, remove lower fixed point, then pick the other value and remove one, then divide it 2. Just like the unknown minus lower fixed point. It's not magical, it's called interpolation. Unknown minus lower fixed point divided by the upper or the other one, the same lower fixed point. Then this one will be equal to the same thing here. I pick this center first, you pick the center here. The center is degrees Celsius minus I pick this one. You pick this one, 0 over. Then I'm going to go and pick the upper side. You pick this one corresponding to this 100 minus pick this one again, 0. That's it. So the same thing you do here, you don't repeat it here. That's the interpolation there. That's the interpolation. So what you do, so you pick the unknown. Whether the unknown is here, pick the unknown, remove the lower, then pick the second value, remove the lower. That will be the denominator. Then equate it to the same thing here, exactly. If you are picking the center, pick the center first. This one minus this. Then divided by this, then you pick this one minus this. That's how you're going to do it. So take note of that, it's very, very important. So if you do that, I'm going to have degree C minus 0, that is degree C. Okay, let us do it this way. K minus, we have K minus 273. This minus 2 gives us 100 is equals to degree C, or degree C minus 0 is degree C. 100 minus 0 is 100. This one will cancel this because they are both the same thing and both are in the denominator. Or have equal to sign between them. So this can cancel this. If there's equal to sign there and they are the same. Or something is equal between them. So next thing we're going to do here would be, we have this is equal to, we have K minus 273 is equals to degree Celsius. So we take note of this. So degree Celsius actually, or we can write it this way. You can see degree Celsius, same thing as Kelvin minus 273. Write it this way. You can also write it this way. If you move on to this other side, we have Kelvin is equals to degree Celsius plus 273. Plus 273. Plus 273. So look at it. Look at it. It's very, very important. Very important. So if I want to convert from Kelvin to Celsius, you remove 273. If I want to convert from Celsius to Kelvin, add 273. For example, now convert 30 degrees Celsius to Kelvin. Convert 30 degrees Celsius to Kelvin. In Kelvin now, it's going to be, if I want to move from degrees Celsius to Kelvin, add 273, we're going to have degrees Celsius plus 270. That will be 30 in degrees Celsius plus 273. That's what we're going to have. Plus 273. So add this on to this. What are you going to have? We're going to have 30 plus this. We're going to have 3. That is 270 plus 30. That is 300. Plus 3 again. That will be. Remember, you do round figure mathematics. This one is empty as 270 plus 3. So 270 plus 30. That will give us 300. 300 plus 3 that will give us 303. Kelvin. See? That's what I'm going to have. That's what I'm going to have. If I say convert, let's say 3 Kelvin to Celsius. Convert 3 Kelvin to Celsius. Now we go from Kelvin to Celsius. From Kelvin to Celsius, you use this formula. So Celsius will now be the Celsius formula. From Celsius to Kelvin, Kelvin should be the formula. For Kelvin to Celsius, Celsius will be the formula. We're going to have this is equal to K minus 273. That will give us, what is the value for K? 3 minus 273. So 3 minus 273 gives us minus 270 degrees Celsius. So that is it. So convert 0 degrees Celsius to Kelvin. That will give us minus 273 Kelvin. So 0 degrees Celsius, also going to do this. Convert 0 degrees Celsius. 1 degrees Celsius to Kelvin. The answer will become convert 0 degrees Celsius to Kelvin. Convert 0 Kelvin to Celsius. And do this too. If I convert 0 degrees Celsius to Kelvin, the answer will be 273 Kelvin. If I convert 0 Kelvin to degrees Celsius, the answer will be minus 273 Kelvin. Go and do it to check we get the answer. You know that is very, very important. So let's do another one. Remember, is the lines from Kelvin to Celsius, Celsius to Kelvin. Take note of that. It's very, very important. Let's do Celsius, and Fahrenheit. Celsius and Fahrenheit. Let's do Celsius and Fahrenheit. Remember, if you want to do it, you draw 2 scales. One for Celsius, one for the other one is what? Fahrenheit. So I'm doing Celsius and Fahrenheit. So the next thing we're going to do here now, the upper pressure is 100 degrees Celsius, that one is 0 degrees Celsius. So it's 212 degrees Fahrenheit. So it's 32 degrees Fahrenheit. So my Chinese is really degrees Celsius, so I'm ready degrees Fahrenheit. Think about that. The next thing we do interpolation. Remember, this is click on node, remove the lower, over, pick the other one, 100, remove the lower, 0. Then you put the same thing here. What you did here, don't repeat it here. The same thing. You have degree Fahrenheit minus 32 over 212 minus 32. Or 212 minus what? 32. So the next thing you're going to do here will be, it's going to be 0 degrees, that's degrees Celsius, 100, is equals to Fahrenheit, minus 32 over 180. So we're going to have that. So next thing we're going to do here, we're going to cancel this out. We're going to cancel this. We have 100, we have 50, that's 5. So what can go into this and this? Check very well, it's got that 20 can go into both of them. 20 can go into both of them. So 20 to 100, we will have 5. 20 to 180, we will have 9. 9 times 20 will give us 180. 10 times 20 will give us 200. So you can organize this to this place. We will have degrees Celsius will be equal to 5 times this. Remember, 5 multiplied everything here. That's the jet there. 5 multiplied everything. So we will have 5 multiplying 32. So I can just put over 9. So that will be 5 over 9 bracket degree F minus 32. This bracket is very important. It means everything here is multiplying it. So this 5 is affecting this and this. That's the way you take note of. So this is the way how to convert from degree Fahrenheit to degree Celsius. That's the way. Then the next thing we're going to do will be, look at it. To move it, now I want to move this one up. The same thing here. I want to move from section not to Fahrenheit. Let me make degree F. The solid from look at it. We already have over 5. We just multiply 9 times this. That's what we're going to do now. 9 times. We're going to say 9 times this one. We're going to have we're going to have 9 times degree F. That's 9 degrees C and over 5. Abi? 9 times this give us. I don't do multiplication now. 9 times this give us 9 degrees C divided by 5. We have this is equals to degree F minus 32. That's what I have there. So next thing we'll have there will be so making degree F the subject of the formula. What we are going to have will be now we're going to move this minus 32 to this other side. So degree F will be equal to 9 degrees C over 5 plus 32. We put some to this other side. So degree F will be equal to 9 degrees over 5 plus what? Plus 32. So please you take note of this. Remember the first one we had when we made the degree C, the subject of the formula, it was degree C is equals to 5 brackets degree F minus 32 over what? 9, or 5 over 9 bracket degree F minus 32. So if you check this and this now, you discover that there's a bracket between these 5 and these two terms here. If you check this one, there's only bracket in the degree C and this 32. So this shows that this 5 is affecting both F and 32 here, but this other 9 is affecting only C, but it's not affecting this 32. So this one is 5 times F, 5 times 32. But this one is just 9 times degree C. That's all. So please take note of that. It's very, this one is just 9 times degree C. That's all. So please take note of that. It's very, very important. So let's say we have to convert or express 30 degrees Celsius in Fahrenheit. Express 30 degrees Celsius in Fahrenheit. What will be the answer? So we have 30 degrees Celsius. And it said move it or convert it to Fahrenheit. So if we want to move from degrees Celsius to Fahrenheit, we use this formula that has Fahrenheit as well as formula. We want to move from Fahrenheit to Celsius, we use another formula that has Celsius as the subject of the formula. So let's move this around to degree Fahrenheit to see what we are going to have. So if you do this now, what we are going to have, now we already know that degree F is equals to 9 degrees C over 5 plus 32. So this will give us 9 times 30, because we have 30 degrees C over 5 plus 32. So this one is going to give us 5 here, 5 here, 6. Now 6 times 9, what are we going to have? 6 times 9, what are we going to have there? Now if you do 6 times 6, we're going to have 36. Then 6 times 3, we're going to have 18. Now 18 plus 36. So what are we going to have there? Or if you do 6 times 10, you're going to have 60. Then minus 6, you're going to have 54. So that will be 54 plus 32. 4 plus 2. That's 2 plus 4. That's going to give us 6. This plus this, 5 plus 3, you're going to have 8. That's 86 degree Fahrenheit. That's what we're going to have. So 30 degrees Celsius is equivalent to 86 degree Fahrenheit. So you just see the conversion. This is how it is done mathematically. Now let's look at how to convert from Kelvin to Fahrenheit and Fahrenheit to Kelvin. So now between Kelvin and Fahrenheit. So remember, we are doing now Kelvin and degree Fahrenheit. That's what I'm doing. Kelvin and degree Fahrenheit. Remember what you do? First of all, draw there are two scales. The first thing, draw there are two scales. If this one will be in what? So I'm being Kelvin. This other one will be in Fahrenheit. So I'll be in Fahrenheit. Then you put there inside the upper and lower fixed point. This one we have 373 Kelvin. That is 273 Kelvin. But this one is 212 degree Fahrenheit. So that is 32 degree Fahrenheit. This one is really in Kelvin. This one is really in degree Fahrenheit. So the next thing, using interpolation, I told you to pick the unknown first. So unknown minus lower fixed point. We're going to have K minus lower fixed point 273 divided by the other one minus the lower fixed point as well. What is the other one here? Which is this 373 minus lower fixed point is now equal to the same thing here, unknown. We correspond to this minus this correspond to this divided by this correspond to the minus this correspond to this. So we have degree F minus 32 all over 212 minus 32. That is all. So the next thing we're going to have now will be, okay, let's sum out this one. So we're going to have K minus 273 over this minus will give us 100 is equals to degree F minus 32 over this minus will give us 180. Then next, 20 to 100. 20 to 100, that will give us 5. 20 to 180, that will give us 9. So we're going to have K minus 270 over 5 is equals to degree F minus 32 over 9. So that will give us, now, I want to make either K or degree F the subject formula. Either will be this or this, any of them. So therefore make K, so the formula here. So I'm going to move out this 5 from here. So just move out 5 from this place. 5 times this, we're going to have K is not equal to 5 times degree F minus 32. Everything over what? Now remember I have minus 273 here. So that is K minus 273, that is K minus 273 is not equal to, remember it's K minus 273. So what is this? I have this over 9. I don't know if you can understand that, you can get that. You see I have K minus 273, so this one is still K minus 273 is not equal to this one times this. We have 5 times degree F minus 32 then over 9. So this minus 273 will now to the other side. We have K to be equal to 5 over 9 bracket degree F minus 32, everything plus 273. So K is mandatory formula. So this is how you convert from degree Fahrenheit to Kelvin. So this is the formula for to convert from degree Fahrenheit to Kelvin. That's the formula we use. Now let's make degree F the solid formula now. So you are going to the same thing, move on to the other side now. Just you cross multiply 9 to this side. This one has been cross multiplied this 5 to this side before. You just use 9 to multiply this. You're going to have 9. You're going to have 9 times K minus 273 times K minus 273 over 5. It's not equal to degree F minus 32. Degree F minus 32. Now we move this minus 32 to this other side. Degree F will be free. So degree F will be equal to 9 over 5. Then K minus 273. It's bracketing because this 9 is affecting everything. Then plus, if this minus 32 plus this, I'm going to plus 32. This is what we're going to have. So this is how you convert from degree, that is from Kelvin to degree Fahrenheit. That's how you do that conversion. So please you take note of that. It's very, very, very important. So let's look at just a simple question now. Let's look at a very simple question. Something that will be very, very lovely for us to solve. Let's say we should convert let's say convert or express convert 278 Kelvin 278 Kelvin to degree Fahrenheit. Convert 278 Kelvin to degree Fahrenheit. Now if you want to move from Kelvin to degree Fahrenheit, use this. This is what I have degree Fahrenheit in the formula. Then if you want to move from degree Fahrenheit to Kelvin, use this one that have this degree, that is Kelvin as the formula. So we are moving from Kelvin to Fahrenheit now. We are going to use this. So let's know that degree F is equals to 9 over 5 brackets K minus 273 minus 273 plus 32. So that gives us 9 over 5. What is K? We have 278 minus 273 plus 32. So this one gives us 9 over 5 times, now 278 minus 273, 8 minus 3, that's 5, 7 minus 7 is 0, 2 minus 2 is 0. So we have 425, that's 5 plus 32. So 5 will cancel 5, so we will have 9 plus 32. Now 9 plus 32, what do we have? 10 plus 32 is 42, that gives us 41 degree Fahrenheit. That's what we will have as our final answer. Now we are going to look at more conversions now. Alright, let's look at this question. Let's look at this question. This question is very, very important. Question 1. Question 1. At what temperature would the Fahrenheit and Celsius scale have the same reading or coincide? At what temperature will the Fahrenheit and Celsius scale coincide? That is, at what temperature will the reading of the Fahrenheit and Celsius be the same thing? That is the first one we're going to look at now. And the Fahrenheit scale and the Celsius scale. Remember the upper fixed point of Fahrenheit. So let's do for Celsius first. For Celsius we have 100 degrees Celsius, 0 degrees Celsius, we have 32 degrees Fahrenheit, we have 212 degrees Fahrenheit. So at what temperature will both of them be reading the same thing? That's what you're looking at now. So this one is reading X, one will be reading X. Both of them will be the same. What will be the value of S? for both scale to be reading the same thing. That's what I'm trying to look at now. I thought temperature with the scale, temperature here, the value here be the same thing. Because this one reading A, this one reading A, B, B, everything will be reading the same thing. So let's look at this. For interpolation, we just say S minus this. S minus 0 over what? 100 minus 0 is equals to X minus 32 over what? 212 minus 32. We have X over 100 will be equal to X minus 32 over 100 over 180. 180. So I'm going to have next thing for the vector times this one times this. So this one is as we have 180x is equals to 100 times this we have 100x. 100 times this we're going to have 3200. So we're going to have the next thing moves to this place, we're going to have 180x minus 100x is equal to 3200. Then 180 minus 100, we're going to have 80x is equal to 3200. So divide both sides by 80, so that x will be free. We will have 80x over 80 equals to 3200 over 80. 0 cancel 0, 80 cancel 80. X will be, because this have minus, I have a negative sign. The negative sign here. So that negative sign will still be with this. The negative sign will still be here. So, another idea. 320 divided by 8 that will give us minus 4. Whether it's big or high or big Celsius. Whether it's big or high or big Celsius. So minus 4 to big or high is really the same thing in big Celsius. Minus 5. Convert minus 4 to big or high to Celsius or convert minus 5 to big Celsius to Fahrenheit. It will be the same thing to minus 40 as well. So let's do another question. Question 2. Let's do another question. Another question. At what temperature will the reading on the Celsius scale be twice of that the Fahrenheit scale? At what temperature will the Fahrenheit scale read 2 times that of Celsius scale? That's what I'm trying to say now. At what temperature will the Fahrenheit give reading which is double of that of Celsius scale? So now they are the same. At what temperature will this one be reading double of this? For example, like this one is reading S, this one is reading 2x. So at what temperature will this reading and this? Will this be reading double of all this inside this place? That's what I'm trying to look at now. For example, let's say we have Celsius. What I'm trying to say, 100 degrees Celsius, and 0 degrees Celsius. So this will have Fahrenheit, 212 degree Fahrenheit, 32 degree of Fahrenheit. I don't know if it's going to be reading double of that x, use 2x. That's what I'm trying to say. At what temperature will the Fahrenheit scale read double of this reading on the Celsius scale? That's what I'm trying to look at now. So the same thing, just almost the same thing. Just the s minus 0 all over 100 minus 0 is equals to 2x now minus 32 all over 212 minus 32. So it gives us x over 100 is equal to 2x minus 32 all over this is 180, right? So you have to multiply. So this times you have 180x is equals to that is 200x 3200. Next we have 180x minus 200x minus 3200. The next thing, 180 minus 200x minus 20 minus 20x equals to minus 3200. So grab us by minus 20. So minus 20, if you cancel this, s will be minus 20 minus this cancel this. That is 160 degrees Celsius. Because x is in degrees Celsius, y2x will be 2 times 160. That will give us 320. So this one being degree Fahrenheit, this one being degree Celsius. So the temperature at which the Fahrenheit scale will be double of that of Celsius scale is either 320 degree Fahrenheit or 160 degrees Celsius. Any of the two. Remember, if you are reading X in degrees Celsius, it will be 2S in degree Fahrenheit, which is 2 times what you have. So our 2S now is in degree Fahrenheit scale. Our S is in Celsius scale. S is this in Celsius, and 2S is this, which will be in what? In Fahrenheit scale. So let's move to other important questions, like let's say number 3 down. A platinum resistant thermometer record 2.00 ohms at 0 degrees Celsius. A platinum resistant thermometer record 2.00 ohms at 0 degrees Celsius and 2.80 ohms at 2.00 ohms at 0 degrees Celsius, 2.00 ohms at 0 degrees Celsius, and 2.80 ohms at 100 degrees Celsius. At 100 degrees Celsius. What will be the temperature when the resistance? What will be the temperature and correspond to the resistance value of 3.00 ohms? What will be the temperature that will correspond to the resistance value of what? 3.00 ohms. Remember, for a platinum resistant thermometer, so you need to remember that for platinum resistant thermometer, so the low temperature, which is X, will be arrow at the low temperature minus arrow at 0, then minus arrow at 100, over arrow at 100 minus arrow at 0, times 100 degrees Celsius. I don't know if you can still remember that. Oh, we used T before, we used theta as well. And you can also use S. You see, the temperature of that S will be equal to resistance at S minus resistance at 0. Remember, resistance at 100 minus resistance at 0 times 100 degrees Celsius. So again, this one is used for platinum resistant thermometer. Or when you have to move from a particular scale to Celsius scale. We also work for liquid in glass thermometer. I'll solve a question like liquid in glass thermometer and then you see it. Then, what's the resistance at the unknown temperature? Resistance at X. Remember they said it's at 0, it's at 100, there is 3 minus. Resistance at 0 is what? It's 2 over. What about the resistance at 100? Resistance at 100 is 2.8 minus resistance at 0 is 2 times 100. Times 100, that's going to give us 1 over 0.8 times 100. Times 100. So that will be equal to 10 over 8 times 100. 10 over 8 times 100. Let's try and see what we can do here. 4 into 8, that is 2. 4 into this, that is 20. Right? Alright? I'm communicating, right? Yeah, that's nice. No, that's 25. 4 into 100 is 25. Sorry about that. 4 into 8 is 2. 4 into 100 is 25. 2 into 2, 1. 2 into this place will give us 5. Now, 5 times 25. What is that? 5 times 25. That gives us 125 degrees Celsius. So 125 degrees Celsius will correspond to 3.00 ohms. So that's how we move from platinum resistant thermometer to degrees Celsius. You see, this is when you want to move from platinum resistant scale to Celsius scale. That's why we use this to take note of that. It's very, very important. So let's look at another question that is still like this, but I now use mercury. Let's say the length of a mercury in a mercury glass thermometer. The length of mercury in glass thermometer is 10 millimeter at ice point. It's 10 millimeter at ice point and 60 millimeters at steam point. At steam point. And what? And 60 millimeters at steam point. Steam point. What temperature in degrees Celsius? What temperature in degrees Celsius will correspond to what temperature in degrees Celsius will correspond to the mercury, which is when it is at 20 millimeters. What temperature in degrees Celsius will correspond to the mercury thread at 20 millimeters? So let's call it at 20x. So if you wish to use this formula for this, it also work. The temperature temperature at ice point is this, at steam point is this, and then S will correspond to, or you just draw, display out. So I'll be the mercury in glass thermometers, then liquid in glass key, then we have Celsius key. So for upper fixed point, at steam point, because steam also means what? Steam also means upper fixed point. So at steam point is 100 degrees Celsius. We had 60 millimeters. Then at ice point, ice means 0 degrees Celsius. 0, that's 0 degrees Celsius. So it's 100 degrees Celsius. So 0 now, 0 degrees Celsius corresponds to 10 millimeter. So what value degrees Celsius corresponds to 20 millimeters? That's what I'm trying to say. That's what I'm trying to say in this place. So let's clear this board now and rectify this issue. So we are going to have, let's take that side I have a node first. Let's use this place. Let's move with this I have a node. You take the unknown, which is x minus the lower fixed point minus upper, or the other number minus lower fixed point. Then take this first one now. What corresponds to s there? 20. 20 corresponds to s. So that is, we have s here, and we have 20 here. We have 100 here, we have 60. 0 corresponds to 10. That's what I'm trying to say. So minus, what corresponds to 0 the other side? That's 10 over 100 corresponds to 60 minus 10. So now give us x over what? 100 is equals to, that is 10 over 50. So I'll cancel this. I'll cancel what? That's 0. I think this will give us 0.2. So this will give us 0.2. So we go out there. It will give us 0.2. So let's go to see where I go out. So, or let us multiply. 100 times, okay, this 10, this 0 will cancel 0. So I'm going to have, this one has to be 1 over 5. So I'm going to have, so 100 times 1, we have s to be equal to 100 over 5. 100 divided by 5, that is 20 degrees Celsius. 20 degrees Celsius. So, 20 millimeters will correspond to 20 degrees Celsius. So let's also use that other formula from continuous resistance key to see if we tally. The x will be resistance. This is now length. Because the length at x minus length at 0 all over length at 100 minus length at 0 times 100 degrees Celsius. That's 100 degrees Celsius. So let's try and see if we have this. What is the length of mercury at the unknown temperature? The length of mercury at the unknown temperature was 20. The length at 0 was what? 10 over. What about the length at 100? The length at 100 was 60. And the length at 0 was 10. And times 100. So 20 minus 10, that's 10. 10 over 50 times 100 times 100. So let's go give us something very nice. Cancel this. 5 here, 1. 5 here, that's 20. 20 times 1, we go 20 degrees Celsius. 20 in degree what? In degrees Celsius. So our 20 millimeters will correspond to 20 degrees Celsius. So let's look at in this same question now. Let's look at this question. The same question. Same question. Now, from this same question now, we have already calculated the temperature decrease that will correspond to 20 millimeters. Now let's look at what temperature, okay, what length of mercury will correspond to a temperature of 120 degrees Celsius. Will correspond to that temperature of 120 degrees Celsius. Look at what I say. I'm trying to say, if this one is 120 degrees Celsius, what will be this length at this 120 degrees Celsius? That's what I'm trying to say. What's the length at 120? This one is already 10. This one is already 60 times 10 times 100. That's what I'm trying to say. So if you make S formula here now, you get the answer. But I want to do it from interpolation. What I say now is we have temperature, let's say 0 degrees Celsius, or let's say we have 100 degrees Celsius, and 120 will be above, 120 degrees Celsius. So this one will be, let me remove this, this is the question. This one will be unknown. What length in millimeters correspond to this? Already know that 60 corresponded to this 100, while 0 corresponded to what? To 10. 0 corresponded to 10. 0 corresponded to 10 millimeters. So let's quickly round off this. You can make X formula here, you get the same answer we get from here now. And let's do it simultaneously. So let's go. Pick on those first. X minus 10 over 60 minus 10 to be equal to 120 minus 0 over 100 minus 0. Why is it that I'm taking the upper side now first, not the center? Look at it. It is not always you must take the center. It's when the calculation. I already told you guys that you should pick the unknown first to make it very easy. If you don't pick the unknown first, you still get the same answer. You do it very well. You pick the unknown first, unknown minus lower, then the other number. Anywhere it is, the other number minus lower. That's how to do it. The same thing here. What corresponds to unknown here? 120 minus lower, the remaining number minus lower. So you pick the unknown first. I think very simple to solve. Now x minus 10 over, that is 50, that equals to 120 over 100. 0 will cancel this. So we have x minus 10 will now be equal to, let's say 50 times this, we have 12 times 50 over 10. This one will cancel this as well. So we have x now be equal to 12 times 5 plus 10. See? So x will now be 12 times 5 is 60 plus 10, that is 70 millimeters. So 70 millimeters will correspond to a length of 70 millimeters with the temperature of 120 degrees Celsius. Have you solved this? I'm going to solve this one. Check if you get the same answer as 70 degrees Celsius. Remember, this one will be 50. 50 will be 50 times 120. Then this 100 will multiply this 2. So we're going to have something like this. Let me just show you what we're going to have. Let me just show you what we're going to have. Put that way I will have. This one is 50. 50 times 120. Then you may even divide by 100 yourself. We just say 50 times 120. That is 120 times 50. Then you divide it by this 100 that's here. Divided by 100. This side will be free from 100 minus 10. That will be, this will cancel this. This will cancel this. It will be 12 times 5. That is 12 times 5 will be 60. Then plus 10 is equals to length at x. That will be 70 millimeters. That is length at x. That is length at x. That's Lx. Length at unknown temperature is 70 millimeters. You just get from this place now. So if I can get it this way, you must know how to solve now very well. Look at it. This one is 50. If you just move on to this place, you divide both sides by 100. When you cancel this 100, you measure one side by 100, you have this. Then you go quickly. Just try your best to make LS formula. You're going to have the correct answer. So let's quickly look at this other question. Just one more question, then we'll have this piece. One more question. So after this class now, go and start converting our temperature scale from one scale of temperature to the other. If I say convert 20 degrees Fahrenheit to Kelvin, go and use all those formulas we derived to convert them. Just go and be solving questions on that temperature conversion. It's very, very important. So let us talk our nose into this question to see what we are going to have. Now, the resistance of a continuous resistant thermometer. The resistance of a continuous resistant thermometer. That's the question. The resistance of a continuous resistant thermometer is 2.00 ohms at ice point. And 2.73 ohms at steam point. What temperature? The continuous resistance scale in degrees Celsius that will correspond to a resistance value of 8.43 ohms. That corresponds to a resistance value of 8.43 ohms. Remember, unknown temperature resistance and the unknown temperature minus resistance at 0 over resistance at 100 minus resistance at 0 times 100 degrees Celsius. Remember that formula? This is used for, we want to go from continuous resistance scale to degrees Celsius. So I just really use it to also run through length of liquid glass thermometer, and it also works. So if this temperature is given and this one is not given, you can also do it. Just use yourself formula, just what I did here. You also get the answer. So let's just compute the values. Theta, what is the hour at theta? The resistance at the low temperature is this. Resistance at steam point is this. Resistance at ice point is this. This one is 0 degrees Celsius is ice point. 100 degrees Celsius is steam point. So we're going to have, what is the resistance at the low? at unknown temperature. So we're going to have 8.43 minus 2 all over 2.73 minus 2, because resistance at the low temperature is this. Put it there. Resistance at 0 degrees Celsius, which is at our ice point, is 2. That's 2.00 is 2. Then resistance at 100 degrees Celsius, which is steam point, is 2.73 minus resistance at 0 degrees Celsius, which is 2 times 100 degrees Celsius. So we're going to have 8.43 minus 2, that gives us 6.43 over 0.73 times 100 times 100. So if you do this very well, you're going to have approximately 881 degrees Celsius. That's what you're going to have. 881 degrees Celsius. So please ensure you practice this thing over and over again. Alright, lastly, you are going to try this question for me now. Shall you do it? Shall I do it? The coil of the wire has the following resistance. The coil of the wire has the following resistance: 3 ohms, 4 ohms, and 6 ohms at 0 degrees Celsius, T, and 100 degrees Celsius, respectively, and 100 degrees Celsius, respectively. You have this, and this, respectively. What is the value of T? The value of T will be 33.33 degrees Celsius. Try your best to do it. Try your best to do this classwork. They're going to have 33.33 degrees Celsius. So we have other questions related to this topic. The next topic we'll be going into will be thermal expansion. What is thermal expansion? If the temperature of the body changes, the body has either absorbed heat or given out heat. Now, if the temperature is constant and heat can be absorbed or given out, that heat is called hidden or latent heat. You get it? I'm still going there, don't worry. Still go there. Now, if a body is absorbing it or a body is giving out heat, there's going to be something that will open to the size of that body. That is going to reduce the size or it will expand. So that's what we call thermal expansion. Increase in size of the body due to increase in temperature. If you decrease the size of the body, temperature will decrease. Exception from water between 0 degrees Celsius to 4 degrees Celsius, because water will experience what we call irregular expansion between 0 degrees Celsius and that's to 4 degrees Celsius. It's what we call anomalous expansion or behavior of water in expansivity between 0 degrees Celsius to 4 degrees Celsius. He said that water that's supposed to increase as temperature increases will now start contracting. So we'll get there. But I'm just trying to introduce something that's what we are going to now. So stay with us. So, and alright, through this temperature, we're going to go into thermal expansivity now.